Ampere's Circuital law. Ampere's Circuital law deals about the magnetic field that is produced by some current. Actually, it relates the magnetic field and the current that is responsible for its production. Its integral form could be written this way: B dl, this is mu naught I. Here, you see, there is a basic difference. You use the circle and fill up this circle, then this is called surface integral. But when you are not filling the circle, this is called line integral. In Gauss theorem, you have to use surface integral, and there you apply the whole process for a given surface. Whereas here we are using line integral, and we are going to apply Ampere's law over a closed loop, not on the surface. That's the basic difference. How to interpret this law? The line integral of magnetic field on any closed loop is equal to the product of mu naught and the current enclosed by that loop. The current will always either enter the loop, penetrate it, or it will emerge from the loop. So, whenever you say the current enclosed by the loop, it simply means either the current entering the loop or the current outgoing the loop. That way, you could say current threading the loop. So, the curve over which this law is applied, that's known as Amperian loop. You see, if symmetry permits, then in place of this one, we could also write mu naught sigma I. But for applying this system, condition is that magnetic field should be uniform on the loop. You see, this law is always compared with Gauss law, that is surface integral of electric field over any Gaussian surface is q upon epsilon naught. Whereas here you say line integral of magnetic field over any closed loop is mu naught into I. When you say integral B dl equal to 0, suppose somewhere you find this statement, it doesn't mean that magnetic field is 0. It simply means that current enclosed by that loop is 0. So, this is also to be kept in mind. When B dl is 0 doesn't mean B equal to 0. When E dl is 0, it is written, it simply means that it is talking about electric field which is conservative in nature. That's why it is quite possible. You do remember that this law itself is always applicable to conduction current, not to the displacement current. If you come across displacement current also and you need the requirement of that to be included, then in that case you have to switch over this law to Maxwell's law. And in that case you will write this displacement current also mu naught IC plus ID. Here in place of simple current you are going to write the sum of the two, that is mu naught IC plus ID, provided you have made sure that displacement current is also involved. You see, Amperian loop will always be chosen in such a manner that the magnetic field is always tangential on the curve on this curve that you have chosen, and perpendicular component must be equal to 0. This total of IC and ID always has continuity over this loop. Gauss law involves electric flux, whereas this Ampere's law always involves magnetic flux.